Okay, here we go. So last time we looked at the algebraic properties of the rational numbers, especially how they form a field under the regular addition and multiplication. Today we're going to look at another way that we can study the rational numbers, and that's by viewing Q as an ordered set. Okay, so let's get started with this, and this will be section 1.3. And I believe the next video will be where we actually construct the real numbers. So let's do it. So definition 6, let S be a set okay, and an order on S is a relation, and we denote it with the classic less than symbol on S, such that the following two properties hold. Okay, the first one, and we'll call these O1 and O2. O for order, of course. The first one is called trichotomy. And it basically says that given two elements, they're comparable in our order. So if X and Y are elements of S, then exactly one of the following must hold. Either X is less than Y, X is equal to Y, or Y is less than X. Okay, that's pretty reasonable. Okay, and the second one is that this is a transitive relation, by which we mean that if X, Y, and Z are set elements of S, and X is less than Y, and Y is less than Z, then X is less than Z. Okay, and you know, there's like a really intuitive way to imagine this. X is here, Y is here, and Z is here, and this is some set S. Don't really care about how the set itself looks, but X is less than Y, Y is less than Z, and together these tell us that X is less than Z. It can be dangerous to draw like a number line like this as a use for your argument, because in reality you don't know what most sets look like. It could be a really ugly set. Okay, and that's what it means for this less than thing to be an order on S. And we will say things like S is ordered by this relation. Yeah, let's make a couple of remarks on this definition. Let's see. So rather than X less than Y, we will just often write Y greater than X. This shouldn't be too strange. It's sometimes just more notationally convenient to do this. And then by this symbol, we read this as less than or equal to, of course. We mean either x is strictly less than y, or x equals y. So basically, this is the logical negation of x greater than y. Okay, so that should make sense. And we know that it's the logical negation because this less than or equal subsumes two of the three possibilities, and x greater than y subsumes the third. And by the trichotomy axiom, that accounts for every possibility. Okay. So what are some examples of ordered sets? Well, N is an ordered set. And we could define the order relation in terms of succession of elements, but, you know, it's not too interesting to do that. You know, we have 1 is less than 2, is less than 3, is less than 4, is less than 5. And it could be like a good exercise to think about how you would actually make this rigorous, like as a definition. You could do it in terms of the succession operator. So for instance, as a hint, n is less than plus plus, which is less than the successor of that. And remember, by like 1 plus plus, we mean 2, 2 plus plus is 3, etc. I think I introduced that in the first video. Okay, and Z is an ordered set. Okay, and to do this, we can make the following considerations. Let x and y be integers. And let's just assume x is not equal to y. Then, well, so if x and y are natural numbers, remember the natural numbers are a subset of the integers, so this is a possibility. We would just say, just use the order from n. Okay, so 2 is still less than 3. Okay, and if x is a natural number and y is not a natural number, well, then y is less than x. Why? Because, well, x is at least 1. X is like one of the elements, 1, 2, 3, 4, 5, etc. And if y isn't one of those, well, that means either y is 0 or y is negative. And that should agree with our intuition for how this order should behave. So y will be less than x. Okay. And if x is 0, 1, 2, 3, etc., and y is not, then y is less than x. And the point here is that this is really closely related to the one above, but this accounts for the possibility that x could be 0, basically. So 0 is larger than every negative number. Okay? Now, so if both x and y are negative, let's note that then x is minus m and y is minus n for some natural numbers m and n. Okay? And let's think about this like in terms of how we want it, right? So -2 is smaller than -1, right? And so on. So what we really want is if m is less than n, then y should be less than x. And if m is less than m, then x should be less than y. And just as an example, like, so say we have 0 here, and then we have x here and y here. Well, this is minus m, and this is minus n. And then m is over here, and n is over here. So you see like the motivation for this definition, right? If m is less than n, well, that's going to mean x is bigger than y because it's further to the right. That's our intuition here for our definition. And that should I'm pretty sure that completely specifies the order on z. It might be missing something, but this should work, okay? Okay, and so z was the hardest one, but actually q is easier to define an order on. So q is an ordered set as well. Given m over n and p over q that are rationals, we say m over n is less than p over q whenever mq is less than np. And where's the motivation from that? You think of like doing cross multiplication. So you multiply through by n, and then you multiply through by q. That's kind of where the motivation comes from here. And when we say mq is less than np, we mean like as integers. So what we've actually done, we've defined an order on q in terms of the order that we already had on z, which is really nice. Okay. I'm going to give another definition. So say S is an ordered set. And that E is a subset of S. Okay, if there exists some element of S, let's call it alpha, such that for all x belonging to E, x is no larger than alpha, we say that alpha is an upper bound for E, or that E is bounded above and I guess I'll put in parentheses by alpha. Okay? And so basically a set is bounded above if there's some element of the ordered set that contains that set that is at least as big as every element in that set. Similarly, well, so we thought about like being bounded above. We should also be able to define what it means to be bounded below. So similarly, if there exists an element beta in S, such that for all x in E, beta is no larger than x. We say that beta is a lower bound for E, and that E is bounded below by beta. Okay, so these definitions shouldn't be too complicated to understand, but maybe let's do a few examples just to consider like how they work. Okay, so let's consider first. Consider the natural numbers as a subset of Q. Is n bounded above in Q? Bounded below? So maybe pause and think about it for just a second. Okay. So, I mean, think about it intuitively. We won't prove this directly yet. But no, n shouldn't be bounded above in Q. Right? Because if you can think of any rational number, you can find an integer or a natural number that's going to be larger than it. And we might prove this directly later, but it's not bounded above. What about bounded below, though? Yeah, absolutely it is. And one thing to note is that there's more than one lower bound for this set. For instance, by 1, 0, minus 1, I don't know, negative 2/3, 9/11, or that, yeah, that maybe not, 6/11, etc. Okay. And it's important to note some of these bounds, so one of these bounds actually belongs to the set itself. So it's important, the moral of this example is that it's possible for a set to be bounded above or below independently of whether it's bounded the other way. Okay, so we have an example of a set that's bounded below but not bounded above. And it's also possible that the bound, should it exist, maybe some of our bounds can belong to our set. Okay, another example. Z, again, is a subset of Q, is neither bounded above nor below. That should be pretty clear. Okay, and now let's consider maybe a little bit trickier of an example. Let's let E equal the set of all these fractions 1 over n, where n is a natural number. So by that we just mean the set containing 1 over 1, which is 1, 1 over 2, 1 over 3, 1 over 4. Okay, and maybe let's think about, and it's the same question, is this set bounded above and or below? And let's think about what this set looks like. So maybe we can sketch it on the on a number line. Okay, and so, well, 1 belongs to this set. 1/2 belongs to it. 1/3. 1/4. 1/5. 1/6. And, you know, these keep getting smaller, but there is a point, though, because we never quite reach 0. So E is bounded above. By, for example, 1. And it's also bounded below by, say 0. Okay, so that shouldn't be hard to believe. And in particular, this upper bound 1 belongs to the set E. And 0, the lower bound that we have provided, doesn't belong to E. Okay. And in fact, it turns out none of E's lower bounds actually belong to the set. Okay. Now, so let's give a definition. We have several definitions today. So let's let S be an ordered set. And suppose that E is a subset of S that is bounded above. Okay, and suppose there is an element alpha in S such that these properties hold. 1, alpha is an upper bound for E. Okay. And 2 is that if gamma is smaller than alpha, then gamma cannot be an upper bound for E. Okay. Well, I mean, this kind of implies that alpha is the smallest upper bound or the least upper bound, and that's exactly what we call alpha. But we actually call alpha the supremum, or the least upper bound. For E. And we write the fact that there is at most one supremum for a set kind of follows from the definition, especially part 2. And if alpha is the supremum for E, we write alpha equals SUP of E. And sometimes we'll read sup E. Okay. And here's an exercise for the viewer if they want it. In fact, I recommend pausing the video right now if you're not familiar with the content and actually doing this exercise. Formulate an analogous definition for greatest lower bound. Or infimum. And just to be clear, this definition, so greatest lower bound should be to greatest lower bound should be to least upper bound what a lower bound is to an upper bound. Okay, so use definition 7 as a hint if you are unsure. But this should be pretty straightforward, I think. Okay, and pause and maybe do that. And once you've done that, okay, let's carry on. So if beta is the infimum, for E, we will write beta equals inf E. That's INF, pronounced inf. Okay, and a couple of more things to note. So if alpha is the supremum for E, and alpha actually belongs to E, which may or may not be the case, as we saw in the examples earlier, we refer to alpha as the maximum of E, and write alpha equals max of E. Okay, and this should make sense. I mean, this is pretty straightforward language, I think. It's a maximal element of E. And similarly, if beta is the infimum for E, and beta belongs to E, well, we refer to it as the minimum of E. And we write beta equals min, M-I-N, of E. Okay. And remember the set. So recall for this set, well, it has maximum of 1. And it has inf 0, but it doesn't have a minimum because 0 doesn't belong to E. So E has no minimal element. And another way to think of that is there's no minimal element of this set, so even as these elements get closer and closer to 0, we can always find another element of our set that's smaller than a given element. Given 1 over n, well, 1 over, in parentheses, n plus 1 is smaller. So it makes sense. And I should say, that 0 is always lower than that. And 0 is our greatest lower bound. Okay, and now we come to probably one of the most important definitions for a good while. And that is an ordered set S is said to have the completeness property or be complete if the following is true. And that is, if E is a subset of S, E is non-zero, and E is bounded above, then E has a least upper bound. Okay, and it turns out that this property of completeness is fundamental. And to see why, let's think about the rational numbers. So I have a question that we will quickly answer after I frame it. And the question is very simple. Is Q complete? And the answer is no. Why? Well, we will prove that now. Okay, so, and we're going to make a throwback to the first video where we proved, I think I called it lemma 1, that there is no rational number p such that p squared equals 2. But we're actually going to show that not only is there a hole where root 2 should be, the problem actually goes a lot deeper. And to show you what I mean, let A be this set. It's the set of all positive rational numbers. That's what the Q plus means. It just means take positive rational numbers, such that p squared is less than 2. And let B be the set of all positive rational numbers such that p squared is greater than 2. Okay. So let's note that A is bounded above by, I don't know, like 3. And B is bounded below by, for instance, 1. And so we want to say that root 2, like we want to say that there is some number, a square root of 2, that should be the supremum for A and the infimum for B. But we know that that's not the case. But the problem actually goes a little bit deeper than this. And to see what I mean, consider some positive rational number. And to this p, associate another rational number q, defined as q equals p minus p squared over 2 over p plus 2. And I promise this is going somewhere. It's not completely arbitrary. And let's actually rewrite this q. So let's rewrite q as, well, so what we do, we multiply through by p over 2 on the left side term, minus p over 2 times p squared minus 2. And then we can do this subtraction, and we end up getting 2p over 2 over p plus 2. 2p plus 2 over p plus 2. And let's actually just write this result, and we will call this we'll call this 1, and we'll box it and set it aside for now. Okay, but then here's where it gets interesting. So q squared minus 2 equals, well, it's 2p plus 2 over p plus 2, all squared, minus 2. And we can expand this, and we get something like 4p squared plus 8p plus 4 over p plus 2 squared minus this term, p squared plus 4p plus 4. And we just keep simplifying this. And the numerator eventually becomes 2p squared minus 4 over p plus 2 all squared. Okay, and now from the numerator, what we can do, we can factor out a 2. And what we're left with is this. Okay, and I'm going to box this in as well. So q squared minus 2 equals 2 over p plus 2 squared times p squared minus 2. And let's think about like where this is going. So 2 is positive, and p plus 2 we're going to square. So that's also going to be positive strictly, since p is at least 0. So this is a positive number divided by a positive number. So this is positive. Okay, but p squared minus 2. Well, the sign of this depends on the value of p. In particular, it depends on whether p squared is bigger than 2 or smaller than 2. Okay, because if p squared is bigger than 2, well then p squared wins, and this is going to be positive. But if p squared is smaller than 2, well then the minus 2 dominates, and this is negative, in which case the whole value of this product is actually determined by the value of p. Okay, so yeah, there's two possibilities. So since p is positive, either p belongs to A or P belongs to B. And let's handle it on a case-by-case basis. So if P belongs to A, we have that P squared is less than 2. And then, well, that's just what it means for P squared minus 2 to be negative. But then from 2, it means that Q squared minus 2 is going to be negative. So Q squared is less than 2. And this shows that Q belongs to A. And also, if you look at it, moreover, 1 implies that Q, which equals 2P over 2, over P plus 2, is going to be larger than P. So given arbitrary element of A, because P was arbitrary, there is another element of A that is bigger than P. Okay, and let's see if it's a similar story for B. So if P belongs to B, well, that just means P squared is bigger than 2, which is the same as having P squared minus 2 is positive. But again, by like a similar argument, Q squared is going to be positive here. Because remember, like all of this depends on the sign of this term in equation 2. And also, Q is smaller than P. So Q belongs to B, and Q is smaller than P. B has no least element. Okay. But now, here's the kicker. So B is the set of all upper bounds for A. And since B has no least element, since the set of all upper bounds for A has no least element, well, that means that A has no least upper bound, no supremum. Similarly, I guess we should be careful because I guess like all the negative numbers in 0 are also lower bounds for B. So this is the set of all lower bounds for B. But, of course, like every element of A is bigger than 0, and every element of A as a positive rational number is bigger than every negative rational number. So it follows that the set of lower bounds for B, has no greatest element. Okay. And what we've actually done, we've shown that there's a subset, namely A of Q, that it's bounded above. Remember, like 3 is an upper bound for A, but it has no least upper bound. So what actually we've shown is that we've shown that the set of rational numbers is not complete. Okay. And that doesn't sound very good, like if you say it, like our set of numbers isn't complete. And what we will do, so we've shown that Q has a few problems, and in order to solve these problems, like filling in the hole where root 2 should be, what we're going to do, we're going to complete Q. So our quest, our duty, okay, to complete Q. And the completion of Q a complete set that contains Q will be called R, and its elements will be called real numbers. Okay, so this is the motivation for what we're doing. And, you know, we've talked about how Q has a lot of holes. Well, I guess we've only talked about one hole in particular. Of course, Q has many holes, right? Root 2 isn't the only hole in Q. For instance, root 3, root 5, root 7, etc. None of these are actually, like, there's holes where all of these should be. But one thing that we can note about Q is that it's really weird to think that it has holes in it, because given two distinct rational numbers, no matter how close they are, we can actually find a third rational number that's between them. In particular, let's just make a remark. Given rational numbers P and Q, if P and Q are not equal, then, well, let's just say, and let's actually just say that P is less than Q. If not, we can just reverse this inequality, right? It would be Q is less than P plus Q over 2, which is less than P. But no matter how close P and Q are, we can always find another rational number that sits between them. And in fact, there are infinitely many rational numbers between them. For instance, 3/4 of the way between P and Q, or 1/4 of the way. right? And we have a lot of rational numbers in here. And we'll make this more precise soon, okay? But, you know, when we talk about the decimal expansion of root 2, and I'm going to put a lot of quotation marks around here, equals 1.4142 dot, dot, dot. Well, this is a rational, so each, if we truncate these ellipses, this is a rational approximation for root 2. And, you know, we can actually get arbitrarily good rational approximations. So the rational numbers are bad, but they're not that bad. And I leave you with this. Next time we will introduce the notion of an ordered field, which is basically, it's an ordered set that also has the algebraic properties of a field and existence of the real numbers. And I won't probably do the full proof of the construction of the real numbers just because it's very tedious in parts, but I think I will do just enough of it to give you an idea of the flavor of the proof. So I think that's all for now. Thank you.